Look up tonight. That enormous sphere of rock hanging in the darkness has been there your entire life, and you have probably never questioned what is actually keeping it there. Since childhood, you were told that gravity is a relentless force pulling everything toward the center of the earth. Drop a stone from your window and it falls straight down. No exceptions, no escape. So here is the question that should be keeping you awake at night. If the colossal gravity of our planet is pulling on a mass of more than 70 quintillion tons every single second of every single day, why are we not all dead? Why is the moon not crashing into us right now? At this exact moment, erasing every living thing from the surface of this planet in a fraction of a second. The answer you received in school was almost certainly an oversimplified story about a perfect balance of forces, or some vague reference to a mysterious outward push. Discard all of that. Those are comfortable explanations designed for people who never intended to look deeper. The truth is simultaneously more unsettling and more beautiful than anything a textbook ever offered you. Here is what is actually happening. The moon is falling. It is in a state of continuous, uninterrupted freefall, directed straight toward the ground beneath your feet. And the only reason it has not destroyed everything is that it keeps missing. It falls constantly and perpetually misses the Earth, colliding instead with empty space. The reason it misses defies the most basic intuitions you have developed about how space and motion work. To understand it, start with something simple. Imagine you are standing in an open field holding a stone. You open your hand and release it. The stone drops straight down. That is gravity in its most direct form, a pull with no detours. Now, instead of releasing it, you throw it forward as hard as you can. The stone travels horizontally, but gravity does not pause or wait. It begins pulling the stone downward the instant it leaves your hand. The result is a curved arc, a parabolic path that ends with the stone hitting the ground somewhere ahead of you. Throw it harder and it travels farther before landing. The logic is straightforward and your intuition follows it easily. But this is exactly where your intuition starts to fail you, because it is built on a hidden assumption. It assumes the ground beneath you is flat. It assumes that no matter how fast or far you throw something, the surface will eventually intercept it. That assumption is completely wrong, because you are not standing on a flat disk, you are standing on a sphere, and spheres curve. Carry this thought experiment to its absolute limit. Imagine climbing a mountain so tall it pierces through the atmosphere entirely and reaches into the cold vacuum of space, where there is no air resistance to slow anything down. At the top, you load an enormous cannon and fire a steel projectile at tremendous speed. It travels forward, gravity pulls it into a curve, and it eventually strikes the ocean thousands of kilometers away. Now you load more powder and fire faster. The projectile travels even farther before curving down. But notice something critical here, something that contains the entire secret of orbital mechanics. As the projectile moves forward and curves downward, the surface of the planet is curving away beneath it. The Earth is round. The ground is literally retreating below the projectile's path. At exactly the right speed, around 28,000 kilometers per hour, the projectile falls continuously, but the curved surface of the Earth falls away at precisely the same rate. The projectile circles the entire planet and strikes you from behind. That is an orbit, and that is exactly what the moon is doing. An orbit is not the absence of gravity. It is not a zone where gravity stops working or becomes weaker. An orbit is what happens when an object surrenders completely to gravity while carrying enough sideways velocity to miss the surface on every attempt. The moon moves through space at approximately 3,600 kilometers per hour perpendicular to the Earth, and simultaneously the Earth's gravity grabs it and drags it downward with tremendous force. But the moon moves fast enough in its lateral direction that the enormous curve of its fall matches the curve of our planet perfectly. It falls around us rather than into us. This corrects one of the most persistent and damaging misconceptions in popular science. When people see astronauts floating inside the International Space Station, the immediate assumption is that there must be no gravity up there. That assumption is completely false. At 400 kilometers above the surface, gravity is still roughly 90% as strong as it is at ground level. The astronauts are not floating because gravity has disappeared. They are floating because the entire space station is falling alongside them at the same rate. The station is in continuous free fall toward Earth, but it is also moving sideways fast enough that it perpetually misses the surface. Every occupant and every object inside falls together, so nothing presses against anything else, and everything appears to float. It is not the absence of gravity. It is gravity operating perfectly, on everything at once. Consider what would happen if you could somehow stop the moon's sideways motion entirely, reducing its lateral velocity to zero while leaving everything else unchanged. The geometry would collapse immediately. Without that horizontal movement, the fall would become vertical. that 70 quintillion ton mass of rock would drop straight toward us, and within hours the entire planet would be an ocean of boiling molten rock. The sideways velocity of the moon is not an interesting footnote to the orbital system. It is the only barrier between our civilization and total annihilation. But if you believe the system is perfectly stable and will continue unchanged forever, you are making another serious error. Gravity is not a one-way relationship, and the side effects of this cosmic arrangement are quietly dismantling our world in ways that almost nobody discusses. The moon exerts a gravitational pull on the Earth with the same force the Earth uses to hold the moon. Mass pulls on mass regardless of which object is larger. And the most visible consequence of the moon's gravitational influence on the Earth is standing right in front of you every time you visit a coastline. The oceans are fluid, they yield to force. As the Earth rotates on its axis, the moon's gravitational attraction grabs the water in our oceans and pulls it toward itself, creating an enormous bulge of elevated water on the side of the planet facing the moon. That bulge is what we call high tide. It is not a poetic phenomenon or a gentle natural rhythm. It is the moon physically deforming our planet from 380,000 kilometers away, pulling billions of tons of water out of position twice each day. But the geometry of this tidal interaction contains a consequence far more significant than the rhythm of the tides themselves, and understanding it requires looking at what happens when two objects rotate at different speeds while gravitationally connected to each other. The Earth rotates on its axis once every 24 hours. The moon takes nearly a full month to complete one orbit around us. The Earth spins dramatically faster than the moon travels. This speed difference has a geometric consequence that most people never consider. Because the Earth rotates so much faster than the moon moves, the enormous bulge of ocean water that the moon pulls toward itself gets dragged forward by the Earth's rotation, ending up slightly ahead of the moon's position in the sky rather than directly beneath it. This means there is a massive elevated mass of water sitting ahead of the moon, and that water has its own gravitational pull. The water ahead of the moon continuously tugs the moon forward in its orbit like an endless gravitational slingshot, pulling it slightly faster and slightly outward with every passing day. In physics, one principle operates without exception. Energy cannot be created or destroyed. It can only transfer from one place to another. The energy required to drag those billions of tons of ocean water around with the Earth's rotation has to come from somewhere, and it comes from the rotational energy of the Earth itself. The oceans drag against the ocean floor as they are pulled around. That friction is enormous on geological timescales, and it is gradually slowing the Earth's spin. Every single day on Earth is a tiny fraction of a millisecond longer than the day before. Our planet is breaking, and the energy it loses does not vanish. It flows directly into the moon through that gravitational connection between the water bulge and the lunar orbit. When you add energy to an orbiting object, it does not speed up in the way intuition suggests. It moves to a higher orbit. Additional orbital energy pushes an object outward into a wider and more distant path around the central body. So the energy the Earth loses from its rotation transfers to the moon and pushes the moon gradually away from us. The moon is currently retreating from Earth at a rate of 3.8 centimeters per year. The orbit is not a fixed and eternal circle. It is an outward spiral, driven by the friction of our own oceans. This means the moon is simultaneously escaping from our gravity and stealing our rotational energy to do it. The system is not in equilibrium. It is in a slow and continuous state of change. The moon is drifting away. The Earth is spinning down, and both processes are connected through the same physical mechanism. The question that follows naturally from this is what happens when the process reaches its conclusion, when the Earth has slowed enough and the moon has moved far enough that the geometry of the system fundamentally changes character. The answer to that question involves a concept called tidal locking, and it points toward a future state of the Earth-Moon system that most people have never imagined. Over billions of years, the Earth will slow its rotation to the point where one Earth day takes exactly as long as one lunar month. The same face of the Earth will always face the moon, just as the moon already keeps one face permanently toward us. Half the planet will see the moon hanging motionless in the sky forever. The other half will never see it again. That might sound like a final resting state, a point of gravitational equilibrium where the system stops changing. But the universe does not grant permanent equilibrium, and a third gravitational player has been present throughout this entire story without receiving the attention it deserves. At 150 million kilometers from Earth, the sun burns with a mass so overwhelming that its gravitational influence reaches us across that incomprehensible distance and deforms our planet every day. The sun creates its own tides on Earth, pulling our oceans and even our solid crust in rhythmic cycles. Solar tides are weaker than lunar tides, but they are continuous and they never stop. When the Earth and Moon eventually reach their tidally locked state and the Earth stops transferring energy to the Moon through the forward water bulge, the Sun will still be there. Its tidal forces will continue creating friction, continuing to drain what remains of the Earth's rotational energy, grinding the system toward an even slower rotation. At a specific mathematical point, the Earth's rotation will slow below the orbital speed of the Moon. This is the critical reversal. The water bulge that spent billions of years running ahead of the Moon, pulling it forward and outward, will now lag behind the Moon's position in the sky. Instead of being pulled forward, the Moon will be pulled backward by the gravitational attraction of that enormous mass of water trailing behind it in the ocean. The Moon will begin losing orbital energy instead of gaining it. An orbiting body that loses energy does not maintain its orbit. It descends. The outward spiral of 3.8 centimeters per year will halt, reverse, and the Moon will begin falling inward toward the Earth. The retreat becomes an approach, and the approach accelerates as the distance decreases and the gravitational forces intensify. As the Moon falls inward over millions of years, its gravitational pull on Earth will strengthen dramatically. Tides will grow from the patterns we know today into walls of water, hundreds of meters tall, sweeping across and reshaping entire continents twice each day. The friction generated within the Earth's crust and mantle by increasingly violent tidal deformation will melt rock from below, triggering volcanic activity on a scale that would make every eruption in recorded human history look trivial. The world will be transformed from within by the gravitational energy of an approaching Moon that has nowhere to go but down. But the Moon's own fate is defined by a geometric boundary that exists in space, invisible but mathematically absolute. Gravity does not pull on every part of an object equally. The near side of the Moon, the face that always points toward the Earth, is approximately 3,500 kilometers closer to our planet than the far side. This means the Earth's gravity pulls on the near side of the Moon with significantly more force than it pulls on the far side. This difference in gravitational force across the width of an object is called the tidal force, and at the Moon's current distance, the Moon's own internal gravity is strong enough to hold itself together against this uneven pull. As the Moon approaches, that differential will grow. The near side will be pulled with increasingly greater force relative to the far side. At a specific distance, approximately 18,000 kilometers above Earth's surface, the Earth's tidal force will exceed the Moon's own self-gravity. At that boundary, which physicists call the Roche limit, the solid rock of the Moon will no longer be able to hold itself together. The structural integrity of an entire world will fail at the geometric instruction of space-time itself. When the Moon crosses the Roche limit, it will not survive as a single object. The differential gravitational force pulling harder on its near side than its far side will exceed the internal strength of the rock holding it together. The Moon will fracture from its core outward, cracking along stress lines that span its entire diameter, and then it will come apart. The destruction will not be a single dramatic explosion. It will be a structural failure spreading through an entire world, shattering 70 quintillion tons of rock into fragments ranging from mountains to dust. What was the Moon will become a ring of debris orbiting Earth's equator, a vast and brilliant band of shattered material reflecting sunlight across a ruined sky. In that moment, Earth will resemble Saturn. The ring will be composed of billions of jagged fragments at every scale, from objects the size of entire mountain ranges to particles of microscopic dust. Seen from the ground below, if anything remained alive to see it, the sky would be crossed by a luminous arc of material stretching horizon to horizon, glittering in the sunlight that still reaches what remains of this world. It would be one of the most extraordinary sights any sky has ever offered. And it would be temporary. Physics does not allow rings to remain stable indefinitely around a planet with an atmosphere. Earth's atmosphere does not end at a sharp boundary. It thins gradually over thousands of kilometers, extending tenuous fingers of gas far into space. The outermost particles of the debris ring would continuously brush against the extreme upper edge of that atmosphere. Each microscopic contact is friction. Each collision with a gas molecule subtracts a tiny quantity of kinetic energy from a fragment's orbital velocity, and an orbiting object that loses velocity descends. One by one, fragment by fragment, the pieces of the shattered Moon will lose their orbital energy to atmospheric friction and begin spiraling inward. The ring that initially appears stable and permanent will slowly drain downward. Over thousands of years, the rate of atmospheric entry will increase as more fragments reach lower, denser atmospheric layers where friction intensifies. What began as a gradual process will accelerate into a cascade. The sky will fill with meteors, then with a continuous rain of fire as billions of pieces of lunar rock enter the atmosphere in an unending bombardment that covers the entire globe every second of every day. The kinetic energy carried by trillions of tons of rock entering the atmosphere at orbital velocities will convert entirely to heat. The energy released will exceed the capacity of the oceans to absorb it. The oceans will boil away, their water vapor rising into an atmosphere already choked with vaporized rock and superheated plasma. The surface temperature will climb until the crust itself melts, reforming the global ocean of magma that characterized the Earth in its earliest history 4.5 billion years ago. The moon will have returned to Earth in the only way that physics ultimately permits, not as a single catastrophic impact, but as a slow-motion, millennia-spanning demolition that rebuilds the planet from the surface inward. The moon will not hit us in the way that imagination typically pictures a cosmic collision. It will arrive as a storm of fire lasting thousands of years, piece by piece, fragment by fragment, reshaping everything it touches until the world we know is gone and something entirely different takes its place. The geometry of space-time, operating through tidal forces and orbital mechanics and the absolute conservation of energy, will have completed a process that began the moment the moon first formed billions of years ago. Every step in that process follows directly and inevitably from the same physics that keeps the moon circling overhead tonight. Stand outside tonight and look at the moon. Do not see a decorative object hanging in the darkness. Do not see the romantic backdrop of poetry and songs. See what it actually is: a 70 quintillion ton mass of rock in continuous free fall toward the ground beneath your feet, missing us over and over with every orbit, its sideways velocity the only thing standing between our civilization and instant obliteration. See it knowing that every night it is 3.8 centimeters farther away than the night before, slowly escaping our gravity by stealing the rotational energy of our oceans. See it understanding that this departure is not permanent, that the mathematics of the solar system will eventually reverse the process and bring it back, and that its return will be the end of the world as any form of life on this planet has ever known it. Everything that has been described here follows from the same physics that governs a stone dropped from a window: orbital mechanics, tidal forces, the conservation of energy, the Roche limit, atmospheric drag. These are not exotic or speculative ideas. They are the straightforward consequences of the same gravitational laws that Newton began describing and Einstein refined into the geometry of curved space-time. The educational shortcut that presents gravity as a simple downward pull is not wrong in a minor technical sense. It actively prevents people from understanding the dynamic, evolving, ultimately violent relationship between our planet and its only natural satellite. The gravity you feel pressing you into your chair right now is not a rope connecting you to the center of the Earth. It is the consequence of the Earth's mass curving the fabric of space-time around it, creating a geometric depression that every nearby object naturally slides toward. The moon orbits not because it is tied to us, but because the mass of the Earth has shaped a corridor through which the moon must travel, and that corridor curves. The moon follows the straightest possible path available to it, and that path curves around us. When we say the Earth is slowing down because of the moon, we mean that the conservation of energy is operating across 380,000 kilometers of space through the physical connection between the moon's gravity and our oceans. When we say the moon is receding, we mean that orbital mechanics dictates exactly where that energy goes. When we describe the Roche limit, we are describing a point in space defined by the ratio between the Earth's tidal force and the moon's self-gravity, a calculation that has been worked out mathematically with precision, not a guess or a speculation. The timeline involved is billions of years. No human alive today, and no human who will ever live, will witness the events described in this final chapter of the Earth-Moon story. But the irrelevance of that timeline to our personal lives does not make the physics less real or less worth understanding. The same forces operating on billion-year scales are the forces that created the tides this morning, that are adding a fraction of a millisecond to today's length compared to yesterday's, that are pushing the moon 3.8 centimeters farther away with every orbit it completes tonight. You were told the moon stays up because of a balance of forces. Now you know it stays up because it is falling constantly and missing constantly, and that this improbable ongoing failure to collide is the most precise and consequential geometric relationship in our immediate cosmic neighborhood. The universe is not a stable and peaceful arrangement of objects in equilibrium. It is a dynamic system of masses curving spacetime, exchanging energy through gravity and evolving toward outcomes that the mathematics makes inevitable even when the timescales exceed imagination. If this changed how you see the moon tonight, subscribe and share this video with someone who still thinks it is simply floating up there. The physics is worth knowing, and the real story is far more extraordinary than the simplified version ever was.